What do running, petting a dog, and playing piano have in common? All three are impossible to do without skeletal muscle. The human muscular system is divided into three categories: cardiac, your heart; smooth muscle, which enables organ function; and skeletal muscle, or how we get around every day. Skeletal muscle is attached to our bodies through tendons, which work as the binding points for the complex torque system that propels our limbs. But how do muscles actually move? Muscles are formed by a hierarchy of bundles, the smallest of which are elongated cells called muscle fibers. The muscle fibers are composed of yet another bundle called myofibrils, which can be over a foot long. Through the sliding filament theory, we know that myofibrils and muscles themselves contract due to the shortening of a unit called sarcomeres. Sarcomeres house actin and myosin filaments in parallel ranks. Actin, which is a two-strand twist of protein, is bound to the edge of the sarcomere at the Z-line. Myosin, thicker protein, is composed of protein strands with protruding heads, which look a bit like a bouquet of golf clubs. The myosin filaments that are bound to the middle of the sarcomere at the M-line stay anchored throughout the contraction process, drawing actin towards the middle. The process of muscle contraction is not the smooth motion that we imagine when we think of our bodies moving. Deep under our skin, muscles are always ready for action. A prohibitory protein called tropomyosin keeps us from constant, uncontrolled motion and enables our skeletal muscles to be voluntary. Wrapped around each twisted strand of actin is a thread of tropomyosin proteins, which cover actin activation sites and keeps our muscles in a resting state. On the surface of each myofilament is a complex system of calcium stores called T-tubules. When an electrical impulse from the nervous system reaches the neuromuscular junction, the portals of the T-tubules are opened up, releasing stored calcium ions. These calcium ions bind to tropomyosin, causing the protein to change shape and exposing the actin activation sites. Now we're ready to move. The myosin heads of each filament rise up and bind with the actin activation sites, creating a cross bridge. The myosin heads ratchet down in an action known as the power stroke, which shifts the actin filaments inward. ATP, the molecule of energy, is required for the head to release from the activation site, and is subsequently broken down into ADP and phosphate ions. The myosin head releases and attaches to the next available actin site, shortening the sarcomere for as long as the electrical signal and calcium stores last. This can happen up to 80,000 times in a single second. This contraction across thousands of sarcomeres in a single muscle fiber creates enough force to move our bodies in all sorts of ways. Here we have a sarcomere. It is the smallest contractile unit of the myofibril. We have the Z-line and the stationary M-line, and the related actin and myosin proteins. Now when tropomyosin moves out of the way of the actin activation sites, the myosin head naturally binds to that site. Then it pulls inward, bringing the Z-lines closer together in a contraction. Now it might only move a fraction of a millimeter every single time the head contracts, happening thousands of times within a second and across hundreds of sarcomeres. It's enough to make our muscles move.